All right, guys, we're doing IGCSE Physics. This is the summer paper of 2015, paper 31. All right, so let's just jump straight into it. Okay, basically this is just a question trying to sort of probe your understanding of sort of speed-time graphs. Is trying to ask to sort of describe the motion. Basically, in this one, we have a graph of sort of, this is a constant acceleration. Basically, because this is the gradient over here is the same as the gradient over here, and therefore the acceleration is then therefore the same. This one, we have one that is decelerating, so the gradient over here is higher than over here. So that's that one. All right. And then we're talking about an object falling off a tall building, and it says sort of state and explain in terms of forces acting, how the acceleration of the object varies during the fall. So I've just drawn a quick little diagram, and basically just before the fall, just before the object is released, you only have the weight acting down, and the object is not moving. So the air resistance, with the air resistance proportional to the velocity. But then as you release it, the drag, right, which is the air resistance, starts to increase. But initially, it is not balanced. The weight is not balanced by the drag, so the object starts accelerating. Eventually, it reaches its terminal velocity when the drag is equal to the weight, so it stops accelerating. So accelerates initially high, and then the acceleration reduces and reduces until it reaches its terminal velocity. Something similar to what might be happening here if we were to extend this and then this were to flatten out. All right, this talks about sort of a large block that's sort of submerged in water. And they give you some values for the pressures acting on the surfaces of this block. Okay, they want you to first calculate the pressure on the top of the block. So you can calculate the pressure, which is just force divided by the area. So we just take force divided by the area. Then they give you the atmosphere, and they ask you to calculate the pressure on top of the block due to just the water alone. So first we had sort of the combination of both, represented by both these arrows. I mean, these look like forces, but if we draw a couple more arrows in, then they look like pressures, and so on. Sorry, they should be equal. And then they say, well, okay, we know the amount here. We also know the result of this. So we basically take the total over here, which is this sort of long arrow represented on the side, let's say, and then we minus off this component there. So we just take the result from here, minus off here, and then we get that answer. And we know that that's all due to sort of the hydrostatic pressure, or the weight of this. And we know the density of the seawater, which is given here. Then they ask you to calculate the depth h. So you just rearrange this equation. All right. So just two reasons why the tension force in the cable is this. So they're saying, well, okay, we've got all of this pushing down in here, this amount here, but why isn't the cable holding that up? So basically, we've got the weight of the block acting down, and then we've got the upthrust from the water. Anyway, the block is lowered that it rests on the seabed. State what happened to the tension in the cable. Well, the minute this sits on the floor, down, let's say down here, you get the reaction from the bottom of the floor. It sits in equilibrium, so the cable doesn't have to hold anything, so the tension drops to 0. All right, this shows an old sort of water-powered device for raising and lowering like heavy things. So you put water in there, lifts it up this side. And this basically, they just go through some very sort of straightforward calculations. The one they say, okay, you've got sort of the force acting here, the weight of the water in the cylinder is acting, here. And and they say calculate the mass of the water. So if we've got the weight, and we can approximate G to, let's say, is equal to 10, right? Then, oh, that's a bad looking 10. Then we can use just the weight divided by the acceleration, or divided by G, to calculate the mass, right? Now we've got the water density. We can then just say, well, the mass is equal to, the volume is equal to the mass times by the density. So we can calculate the volume. Okay, then they go on to ask, like, the piston moves a set distance, calculate the gravitational potential energy lost by the water. All right, which is just going to be mgh. So we got the mass, we've got G, we've got the heights, stick those all in. And then they go on to say the heavy load lifted by the piston gains this much energy of gravitational potential energy. Calculate the efficiency of the device. Okay, well, we basically contrast this answer to this answer. And looking up at the answers themselves, it just basically illustrates that the device only has a 30% efficiency. So it's just basically output, which is this guy over here, divided by input, which was the number that came out of here, which was around 300 and something. And you got roughly a 30% efficiency, which was pretty decent for devices back then. All right. Okay, so this is just contrasting the molecular structure of liquids, or contrasting that of a solid. And you just need to talk about stuff like they're sort of, solids are bound to each other. Liquids are sort of moving and random and sort of folding over each other and so on. And you could say that, like, liquids are maybe, like, slightly further apart than the sort of molecules of liquids are slightly further apart than that of solids. There's a whole range of things you can go on to say. And then it says, explain in terms of energy the process which takes place as a solid at its melting point changes into a liquid at the same temperature. It's just sort of like the latent heat is probably the key word to be used here, sort of like the latent heat of, changing states. All right, then they talk about this sort of all leads on to this question here, where during a severe storm, a layer of snow forms on the body of an animal in a field. The snow and the surrounding air is at 0 degrees. The snow begins to melt. Basically, what they're assuming is that, this is sort of a latent heat process in which even though the snow is initially melting, it just stays roughly at the same temperature. And then the specific latent heat of fusion is this. That's sort of the key word to help you suggest that that's what's happening. Then they say calculate the thermal energy needed to melt the snow. So basically, you just sort of take your latent heat of fusion, multiply it by the weight, and you should get then the amount of energy needed to melt the snow. And the poor old animal is having to create that energy. Okay, the animal derives its energy from its food to maintain its body temperature. State the energy change that takes place. That's basically just like chemical to thermal. All right. And then they just ask you to sort of state what is meant by the specific heat capacity. So it's the amount of energy required to raise 1 kilogram by 1 degree, for example. All right, a student carries out an experiment to find the specific heat capacity of aluminium. He uses an electric heater and a thermometer inserted into separate holes in an aluminium block. The following data are obtained, so on, so on, so on. Calculate the value of the specific heat of aluminium given by this experiment. Let's see what we've got here. Okay, we've got the power going in. We've got the weight. The mass. We've got the time. So we can basically take the power, times it by the time, equate that to the specific heat multiplied by the mass multiplied by the change in temperature. Rearrange this for this, plug in these numbers, and you should get your answer. All right, in the experiment, no attempt is made to prevent loss of thermal energy from the surface of the block. All right, suggest 2 actions that the student can take take to reduce the loss of thermal energy from the surface of the block. Well, they're basically, I think earlier on it's mentioned, it doesn't mention anything to do with, so there's no insulation is one, so you could insulate it. Or you could do this experiment with a lower temperature rise. In other words, if you keep, let's say, the power the same, you could reduce the time, or you could keep the time the same and reduce the power. Basically, you don't want this delta T to be high, because effectively what you want to do is you want to reduce the temperature difference between the block and its surroundings to stop sort of heat loss to surroundings. So the basic answer for both is to just reduce the heat loss to the surroundings, either by changing up your parameters or by adding additional insulation. And most likely the best answer would be to do both. All right, this is just a quick question about waves. A wave in a tank. Okay, so you've got like sort of like a wave in a tank with 2 regions where the wave travels slower or faster, and then it shows you, sort of illustrates these sort of wavefronts. And the first question is, so using like an actual, so imagine this is the scale drawing where you've got 1 to 4. Take measurements of the scale diagram to determine the wavelength of the water waves as it travels through the region. So you just get out a ruler, measure this, use the scale, and you should be able to then get your wavelengths. All right, so the speed of the water of the wave is faster. In the faster region is this. Calculate the frequency of the wave. So you just use your like wave equation and use your speed and your measured wavelength to back out the frequency. All right. Okay. Draw lines that indicate the position of the wavefronts of the water waves in the slower region. All right. So they'll sort of, here's a bit of a bad drawing, but these lines should be like nice and parallel and swept slightly backwards. And that is, if you imagine like this wavefront over here, when it first sort of entered this region, it's had to travel a longer distance as opposed to a point over here. And so because this region is slower, this sort of allows the wave to sort of move faster here before it hits this region. And this one has to then get swept back more and more and more. So that's why these lines are sort of inclined backwards a bit. All right. Okay, state what happens to the frequency of the water as it passes into the slower region. Oh, the frequency remains the same. All right. Okay, let's see. Okay, it just represents the object O placed in front of a converging lens. All right, so state a full description of the image at eye. Okay, well, it's a lot of information given to us in this diagram. Basically, sort of this is pointing up, so the image is upright. It's larger than the objects, so you can just write larger image, and it's a virtual image, and that is because it's sitting on this side of it. All right, using the letters in figure 7.1, identify the focal length. Basically, it's just from R to S, because this is where we get that focal point intersecting the principal, this ray intersecting the principal axis. And so that is our focal length. All right, draw an eye suitably placed to view the image. Well, it just has to be on the right-hand side. So we can actually see this virtual image that is magnified. All right, on figure, okay, so then we've got a slightly different scenario here. Figure shows an object O placed to the left of a converging lens. A principal focus of the lens is at position marked F, right? And it says, draw two rays to locate the image of the object and draw the image. So actually, I forgot a little bit of information here. So here's the image. So basically, we can draw one ray coming out here, going through the principal focus. And then we can have one going through the center of the lens that doesn't get refracted. And where these two intersect, we'll locate the image. And you notice that the image is now flip-flopped, it's upside down. So it's, and it's at this location. And then just it says draw another ray from the tip of O to the image. We could probably just draw that one in there. All right. Okay, this is just showing basically a bar sitting over one of these coils. And then you lower the bar in as you move it in. They are sort of what during the movement, an EMF is induced in the coil. The meter shows a deflection to the right and then turns to 0. Okay, so and then explain why this EMF is induced. Well, it's just like basically the flux lines of the magnet are intersecting the coil and then producing a current in here. And then state what happens to the needle when the magnet is released from rest and is pulled up by the spring. Well, because it's now going in the other direction, the needle, if it was initially, which way was it initially going? Okay, so if it was initially going to the right, now it's going in the opposite direction, so then again gets deflected to the left. And then continues to sort of oscillate up and down. So what happens to the needle? It sort of just then starts sort of bouncing left and right because the magnet is going sort of backwards and forwards in and out of this thing. So the needle just sort of goes sort of like left into the right, left into the right. Okay, this is a quick question about transformers. For the first one, you just have to plug in the equation for your transformers, your primary and secondary windings, primary and secondary voltages, chuck them in, and you can sort of back out the number of terms. Then it asks you to calculate the power input into the transformer. So if we've got the current input, and we've got the voltage input, we can then figure out the power. Then it says 90% of the power input to the transformer is transferred to the lamp. So not all the power is transferred. Calculate the current of the lamp. So we just have to use the same equation as above, but instead of using the full power transform, we just say 0.9 of it. So 90 over 100 of the power in the transformer, hence the T that goes into the voltage at the lamp, and then we should get the current in the lamp. Let's put a little L there. Okay. Now we've got another one here where we've got basically a thermistor and two resistors. And basically, they're saying at a certain temperature, the resistor has this value, the thermistor has this value. And it says calculate the resistance of the thermistor and this resistor. So we just like basically just use our parallel resistor equation to calculate the combined resistance of this. Then we chuck that in, we chuck that combined one in series with this one over here. We get the net resistance. Then we can use that to calculate the current given this potential difference there. Then from this current and this resistance here, we can calculate the potential difference across the second one over here. because this is now one in parallel, combined into one resistor. Now it says the temperature of the thermistor is increased so that the resistance decreases. State the effect of this change in resistance on the current through the 500 ohm resistor. Explain your answer. Quite simply, if this system is, if this combined resistor here is reducing in resistance, the overall current increases, and therefore the potential difference, the potential drop across this resistor also increases. All right, this is just a question about electric fields. Shows two parallel plates connected to a very high voltage supply. The left-hand plate is positively charged, the right-hand plate is negatively charged. Draw the electric field pattern produced between the charged plates. Use arrows to show the direction of the field. So it's from positive to negative. These should be roughly parallel and of equal spacing. All right. So we've got, and then it says a light conducting ball is suspended by an insulating string. Shows the ball in the middle of the gap between the two plates. On figure 10, show the distribution of the charge in the ball. So I've blown it up a little bit because it's a bit hard to annotate it at that size. But basically what you want to show is that one side has an overall net positive charge, and the other side has an overall net, so the right-hand side has an overall net positive charge. The left-hand side has an overall net negative charge. However, the charge of the entire combined ball, the overall charge of the entire ball is still the same. What's happening is because sort of the charge here is negative, it's pushing the electrons over to the left a bit. And in this case, is drawing the electrons slightly towards it. However, there is no actual, like the ball started off neutrally charged, and shouldn't therefore gain any overall net sort of charge. And this is just what you're trying to sort of illustrate with this diagram. And then the ball is displaced to the left, and then oscillates backwards and forwards between the two plates. All right, basically. And as it oscillates backwards and forwards, it sort of transfers charge. When it touches this, it gains an overall positive charge, dropping off some electrons on this side. Then once it's got this overall positive charge, it shoots across back to the right-hand side in this process, and then picks up some more electrons, and it just sort of transports these electrons backwards and forwards. And it says calculate the average current produced by this process. And well, we basically know how much charge it transfers each time, and we know how often this happens. So we just take the charge, we divide it by the time, and we get the current. So that's quite an easy question. All right, state the nature of X-rays. Just high energy electromagnetic radiation. And we have a beam of particles, so alpha particles and beta particles, passes in a vacuum between the poles of a strong magnet. Compare the deflections of the paths of the two types of particles. So the first and most obvious thing is that they will, since the alphas are positive and the betas are negative, they'll deflect in opposite directions. We can then also say that they're both curved paths. And we can say that, let's say, the beta particles should sort of curve more abruptly, or sort of be diverted in a more strong fashion, because they're far lighter. And if the magnetic, since they're both experiencing the same magnetic field, the betas should curve more because they're just basically lighter. All right, then it goes on to say a beam of beta particles passes in a vacuum through an electric field, as opposed to a magnetic, between a pair of oppositely charged metal plates. Describe the path of the particles. Well, if it just sort of curves towards the positively charged plates, since the betas are negative, it'll be attracted to the positive. So it'll do the same sort of similar thing where it curves, but you can be more specific and say it curves towards the positively charged plates. Okay, then we've got a quick one on sort of isotopes. So the nuclear equation shows the decay of an isotope of polonium, and basically state the nature of X. Well, X is an alpha particle, so it's alpha decay, because this is, you know, basically the same as a helium atom, just with the electron stripped off. So you could say that X is a positively charged, you could say it's a +2 charged alpha decay. And then then it asks you to calculate A and Z, and that's quite simple. All you have to do is add these two top numbers up and add these two bottom numbers up. So for A, it's just going to be 210, and for Z, it's going to be 84. Thank you very much, guys. Hope this was helpful, and we'll see you guys soon.